We're going to change up the format a little bit here in that these will be 3 12-minute presentations, then followed by a question and answer period. So if you'll please write down your questions and save them for then, it would be great. Later on this morning, we're going to talk about the contestants with their actual products that are being marketed. But first, we're going to do an overview. And our first presentation is Dr. Rombenso. He got his PhD in Southern Illinois University here in the US. He's now with Cicero. He's going to talk about fish oil replacement in marine fish.
Okay, good morning, everyone. It's a pleasure to be here. So today I'm going to present some recent research that I've done in Southern Illinois University in Carbondale in collaboration with Hub Seaward Research Institute and Virginia Tech. Some other work from the Autonomous University of Baja California in Ensenada, Mexico, and some work from the University of São Paulo, Brazil. All right, so just a quick overview, just a brief background. I'm going to talk about the fatty acid essentiality in marine fin fish, then follow for the fatty acid composition of the dietary lipid sources, and the benefits of the saturated and monounsaturated fatty acids, the SFA and MUFA-rich lipids, and a quick summary. So we all know the value of fish oil in aquafeeds, especially they are rich in LC-PUFAs, the long-chain polyunsaturated fatty acids. Here you can see on the top right illustration of the bioconversion pathway, which most of the marine carnivorous fish, they have limited capacity to synthesize these nutrients. And the big question is whether all these LC-PUFAs, they are equally important or not. In this table, I listed some of the major lipid sources, their LC-PUFA content, the dominant fatty acid groupings, and the price. The ones highlighted is the one I'm going to be addressing in this presentation. And in terms of fatty acid requirements, there are 3 components that are going to be mentioned too in terms of physiology, optimum growth and health, and the nutritional quality. So to start things off, this first trial was done with California yellowtail. We fed the juveniles with 12 diets, a fish oil control diet in blue, a soybean oil negative control diet in green, and we used this negative control diet, we supplemented with ARA, EPA, DHA individually, a combination of DHA and ARA, and combination of all. So to make easier, the colors, light colors means 50% supplementation, darker colors 100% supplementation. And the results are summarized in the left, as you can see. On top we have weight gain, and in the bottom FCR. So I summarize in 4 stages. When you have a control LC-PUFA, you're going to have a regular growth and FCR. When you have a lack of LC-PUFA, you're going to have impaired growth performance. Stage 3, you have an optimum LC-PUFA, and we can see the combination of 100% ARA and DHA. We see that things get better, so we have an optimum growth and FCR. However, when you have an excess of LC-PUFA, you see that the growth cannot be efficient, and the FCR, however, if you're talking about nutritional quality, might have some important points there. On the left, we have the dietary and lipid and fillet fatty acid composition. As you can see, the fillet really mimics the dietary fatty acid composition, and all the soy-based diets, they accumulated the 18, 2, and 6 is the key fatty acid in the standard soybean oil at the expense of LC-PUFAs. So in this study, we can say that soybean oil could completely replace fish oil as long as we added enough LC-PUFA in the diet, and this study, we highlighted the benefits of adding ARA and DHA in the diets. A follow-up study with the white sea bass and other marine carnivorous species. We test fish oil control diet, standard soy oil diet in green, and a saturated soy, the SFA soy, in pink. And both of these diets supplemented with DHA. In terms of performance, no surprise in terms of the standard oil, but with the SFA, if you can see, it performed better than the fish oil control diet, which is very interesting. If we look at the dietary and the fillet fatty acid composition, again, no surprises in terms of the 18, 2, and 6 with the key fatty acid, the soybean oil. But if we look at the 18-0, we see that it was not accumulating the fillet. Okay, this is suggesting a LC-PUFA sparing effect, which means that the LC-PUFA, they are being more bioavailable and in result, they are deposited in the fillet. This is a new study we designed with Cobia. So we fed fish oil diet and greater levels of ARA in SFA-rich lipid diets. And as you can see, with more ARA, you improve performance. And the interesting, if you look at the fillet fatty acid composition, you see that with 1.2 ARA, you increase the deposition of DHA and the total LC-PUFA. So this was quite interesting. In terms of histology of the liver, you can see that a higher ARA, 1.9%, you have higher vacuolization. So consequently, you have apparently less hepatocytes. But this was very interesting because we could support our hypothesis that ARA is important in fish nutrition and also the deposition of LC-PUFA in the fillets. So this one is a standard fish oil, partial fish oil replacement with pompano. We try a variety of alternative lipids. So we didn't have any effect on growth because we have certain fish oil in the diets. But here is just to highlight how the fatty acid composition of the fillet is distorted with the alternative lipids you are using. So we can see the quality line in one, the circle, the blue circle, it's the fatty acid profile of the fish oil control. So everything above that means that it's in higher levels, everything below, lower levels. So you can see that most diets, they have reduced levels of LC-PUFA, and among all the different lipid sources, the SFA is the best one. So we have it's more similar to the fish oil control. Next trial, we evaluated 8 diets in pompano, fish oil control, again in blue. Now with a beef tallow, which is a good example of saturated and monounsaturated fatty acids. We added with individually APA, DHA, combination of both at 50 and 100%. Just to highlight there on the top right, as you can see, the difference of DHA and EPA in the diet. So the control has over 40 grams per kilogram feed, and the negative control only roughly 8. And the question is this going to be enough to provide optimum growth and health? And the answer is yes. So never doubt about the SFA and mufa-lipid, rich lipids. So no effect in performance. If we look at the fatty acid composition, we have some LC-PUFA sparing effect too. So here I just illustrated the APA and DHA. So you see they accumulated also in a diet in similar levels at the fish oil control diet. So to validate all this trial, this work, which has been part of my doctorate there at SIU, when I moved to Mexico, we started doing some work to follow up with totoaba. It's an endemic marine carnivore species there. So very similar design. We have a fish oil control diet in blue, a beef tallow. This time we had a lot of poultry byproduct meal, which was very rich in lipids, have a residual lipid of 15%. So that's why I'm going to talk a little later about the implications of the results. But in terms of performance, the same. We have no difference. The fatty acid composition, we saw a limited LC-PUFA sparing effect because they have higher levels of 18, 2, and 6 in the diet, coming from the poultry, the feed they're eating. To highlight that we have no changes in their health assessment, we did overall over 12 blood parameters, only we have 2 difference in 2 of them. A follow-up study with the same diets with yellowtail, we have similar results, no major effects. Again, blood parameters, they were pretty similar across dietary treatments. And actually these slides, I'm presenting 2 studies. The regression graphs illustrate, so it was a study with yellowtail that we did different blends of soy, vary from saturated to high concentrations of C18 PUFA. And one thing I wanted to highlight here is that the regressions show clearly that as more C18 PUFA you have in the diet, you limited the deposition of LC PUFA, I mean DHA, EPA, ARA in the fillet. But with the SFA, higher levels in the diet, we increase the bioavailability and also the deposition in the fillet. These are just some ongoing work. I have been collaborating, no time to present everything, but some different trials. And one is very interesting. They're doing a whole grow-out trial with totoaba using fish meal and fish oil-free in raceways. And just to sum up, in terms of fatty acid essentiality, we can say that DHA and ERA are the primary drivers. In marine fin fish, DPA is also important, but in another level, in minor amounts. The fatty acid composition of the lipid source is very important in terms of bioavailability of LC-PUFA and how they are deposited in the fillet. So the SFAs apparently be the most advantageous in this context, followed by MUFAs and C18 PUFAs in the end. And some important topics we're investigating is to try to find optimal fatty acid ratios. And also I think it's very important for us to access and establish thresholds. What is a good blood parameter or a good histology in fish? So thank you.